So last time we were looking at the derivatives for the exponential functions. I think I just showed you the general rule, probably give one example. I'm going to do a couple more of those and then I'll show you integration. And then we can do worded problems that involve logarithms and exponential functions. These are the applications of the exponential logarithm and the integration differentiation. Oh, by the way, I don't know if I think I mentioned it in Cal 1. I don't know if I've mentioned it in Cal 2 yet. Maybe I did earlier at the start of the course. But whenever you differentiate, you're getting a rate. That's what the word differentiate. it gives you rates. Generally, when you differentiate in terms of time, you're getting how fast something is increasing or decreasing, or if it stays constant. When you integrate it, now it goes back to the production function, you can call it that. So, well, I'll put it more in detail once I word problems. But for now, let's go to the derivatives. We'll do a couple of them, see number one first. So finding the derivatives of each of the functions I'm going to give you. The first one is differentiating something simple, 6 to the 2x. I'll start at number one in the textbook, 6 to the 2x. So to differentiate this, we simply use the rule. The rule says differentiate the function in power, which is going to give us 2. Differentiate 2x to get 2. Next, we put back the same thing, 6 to the 2x. And the last thing is to multiply by the natural logarithm of the whatever value is right here. We'll call it a. In this case, it's 6. So we'll get 2 times 6 to the 2x times ln 6, which we can simplify to write like this, 6 to the 2x times ln 36. So remember that the 2 here can place in the power. Both we could put the whole thing in the power, but the 2 looks nice over here rather than all that raised to 6 to the 2x. Good. So that's a simple one. Let's do a more interesting one now. We're going to differentiate in terms of x. Well, the book has z. I'll stick with the x. 3 to the x ln x plus 5. So they can say this is a product. So we're going to use the product rule. Differentiate one at a time and multiply where necessary. So we have, this is an exponential function, and the second one is a logarithmic function. So we can do any one we want first. I'm going to start with the 3 to the x first. So differentiating 3 to the x, we differentiate the power, which is x. That gives us 1. I'm going to write the 1. You don't have to. Put back the 3 to the x, and then multiply by ln 3. Now we have not differentiated this one yet. Remember, the product rule is differentiate one, multiply by the other, and then put back the first one and differentiate the other one. So we have to multiply by this as well. So times, let's use brackets this time so we can differentiate them. Ln x plus 5 plus, now we'll leave the 3 to the x alone. So remember, it's a product now. This one times that one. Product rule says differentiate one, multiply by the other, then differentiate the other one, multiply by the previous one. So I differentiated the 3 to the x, which gave us the differential derivative of x is 1. The derivative of 3 to the x, differential derivative of 3 to the x is differentiating the power first, which is going to give us 1. Put back the 3 to the x, remember that doesn't change, and then multiply by ln of the number that's right here. Remember, I think the formula given was a to the x. You differentiate that, you're going to get, I think a to the f of x I'll give you. You get f prime, you get the a to the f of x again, and then ln a. That's what we're doing right now. The x was the f of x, differentiate f of x, which is x, we get 1, multiply by 3 to x, and ln of 3. And we put back the thing that was right here. We're going to use that one now. So put back the 3 to the x, and differentiate ln x to the 5 now, ln x plus 5. which is not hard. It's just going to be differentiate x plus 5, which gives us 1 at the top, and put x plus 5 at the bottom. So those rules, have to remember them. For the exponential function, differentiate the function, put by the agent f of x, multiply by ln a. For the logarithmic function, differentiate the function, put to the numerator, and put by the exact function in the denominator. So let's simplify everything now, make it look nicer. 3 to the x occurs twice, so we can just take it out. Factor it out, make it look nicer. Now, do not make a mistake. I've seen students make this mistake of, okay, ln 3 times ln x plus 5, multiply the 3 and x plus 5. That is wrong. Don't make that mistake. Create your own rules, There's a rule that says ln x plus ln y is equal to ln x times y. There is no rule that says ln x times ln y is equal to ln xy as well. That's wrong. So please don't make that mistake. You can't do anything with this. Afternoon. You can't do anything with this except to leave it as it is. Or work them out if you know the numbers or don't know the x. So we're just going to leave the ln 3 times ln x plus 5. Should I put ln 3 brackets instead? Ln x plus 5 already has something bracketed. I don't want so much bracket. Ln x plus 5 plus 1 over x plus 5. Yes, the most that I can do. Erase this. Any questions about that one? If not, we continue. So maybe the 2 more and then I'll show you how to integrate it. The integral is just really substitution, as long as you know the rule of what you're going to, what you're coming from. So number 3. This one is a nice one now. We have y equals 10 to the x squared. So 10 to the x to the 2. Yes. Plus, watch this one now. X squared to the 10. That's trying to trick you, but just want to make sure you see the difference between two things. I don't think it's that much different, that much difficult for you to see, not see the difference. But for this one, simplify it first. The 10 to the x squared, you can leave it alone. But the x squared to the 10 is just x to the what?
20.
20, correct. X to the 20. So it's multiply the powers. All right. You could use it as it is now. If you wanted, you could use the chain rule. You get the same answer. Different. As a matter of fact, I'm going to do both ways. This is the same thing. All right, so let's differentiate the y now with respect to x based on the rule I just gave you. So we have a number raised to a power. That's a to the f of x. So differentiate the power. We get 2x. Put back the 10 to the x squared. Don't subtract anything from it. Remember the a to the f of x stays the same. And then lastly, we get ln of the number, which is 10, not the 2. I've seen that mistake, the people put ln 2. Remember, it's ln of the a. The a is down here, where the 10 is. All right, so finish with that one. Plus x to the 20 is just 20, x to the 19. I'm talking for that. Multiply and subtract. So I'm going to use the chain rule to show you that if you've done this one using like this, you get the same result as you see right here, the 20x to the 19. All right, before I do that, let me simplify this. You can't really simplify much, The most you could do is get ln 100. Like, well, you could actually put it like that if you want. You could do 10 x squared ln 10 to the x. Beg your pardon, 100 to the x. Could do that if you want. Plus 20x to the 19. That's the most I can see to make it look decent. Yeah. Oh, do not make a mistake of multiplying 2 to the 10. This 2 to the 10 right here. If the numbers are different powers, you can't multiply them. Just make sure you're clear on that, because I've seen it happen before. Like people get 2 times 5 to the 4 and say, okay, that's equal to 10 to the 4. That is incorrect. Watch out for that. Remember the rule you learned in college, which was x to the a times x to the b is equal to x to the a plus b. So you see, in this case, the powers are different,
The bases
but
are the same,
the bases are the same.
but if two different bases, they can't work.
There you go. So if it's x to the a times y to the b, I'm going to kind of think with that, which is exactly what we have right here with these two things. The power for the 2 is 1, the power for the 5 is 4. We can't combine them. If it was 2 to the 4 now times 5 to the 4, that's 10 to the 4. But the powers are different, like this 2 right here and this 10 right here. Leave them alone. So everybody understand how I got the ln 100 to the x?
So you would put the 2x power.
Right, the 2x in the power for the 10. That's right.
Sir, can you go over the 20x19?
20x19. Oh, you see, because I do so much hard things, you forget the easy ones, you know. I'm going to show you. Watch. Remember the basic rule of differentiation, multiply by the power and subtract it. So, where's the question? I was sit here. X to 20. 20 times x, 20 minus 1. Multiply, subtract.
No, sir, we know that part, sir, but
Oh, you mean how I get from this to this?
no.
What
All
then?
right, so like for the 10x squared, we go to the differentiation method, sir. So why with the x20 we don't do that?
You mean the exponential function differentiation?
Yeah.
Because exponential function differentiation works when you have a number raised to a function. It's the function raised to a number.
And also,
Okay, I
20
understand.
to the 19, you're basically differentiating using the power rule.
Right. But he was wondering why we didn't use the exponential rule.
Okay.
But exponential rule only works when you have a number constant raised to a function. So this time it's a function raised to a constant.
Get
It
it,
was,
sir.
what was that? Was 0?
Yeah, man, yeah, man.
You get it now?
Yes, sir, yes, sir.
All right, cool. All right, so let me differentiate this thing using the chain rule quickly. So you see, you get the same result as that. X to the 2 raised to the 10. If we differentiate this now, we're going to get, remember the chain rule says multiply by the power, which is the 10 right here. We'll get 10. Differentiate the function inside the bracket, which is x squared. So differentiate x squared, get 2x. Put by the same function, x squared, and subtract 1 from the power. So you get 9. Remember, that's the normal chain rule. If you have a function, raised to a power, multiply by the power, differentiate inside, put by the same function, subtract 1. Now let's simplify that. 10 times 2 is 20. X, and we have x squared to the 9, that's x to the 18. So you see the x times x to the 18 is x to the 19. Just takes longer. That's why it's better to simplify it. Sometimes it makes it faster. Before you differentiate. If you can simplify it. So you get the same result. So whichever way you would have done it, you'd have gotten the same result. All right. That is another example. Let me see if I see anything else here that's interesting. This one does looks hard, but it's not hard. All right, the 2 more. That was supposed to be this second to last one. Maybe one more. I don't know if anybody wanted this. Let's take it off. Number 4. Oh, I know you guys don't like trig functions. Let's see one here. Y equals sine squared x plus 2 to the sine x. They like putting these little things for, so you can see the difference between them, but you know, these are pretty straightforward. Differentiate the y. Let me see if you guys can do that.
Let me go try.
Oh, yeah, I was gonna say that. I want to see if you guys can figure out these two.
All right, sir, fix it up first now.
You can do that this, but if you want to write the other way, all right.
Okay, so sine x r squared plus 2 to the power of sine. Yeah, you fix it up first. All right. All right. All right. So the derivative of sine x is cos x.
Mm-hmm. Am I right that? All right.
Sir, I feel like it's better we keep it. The sine squared, keep it as sine squared x.
It's the same thing, whichever way you do it. So whichever one you want to look, you can just go straight down after that. Hold on. Hold on. Hold on. Hold on, Akeem. What would you have done if you did it this way? What would the answer have been down here, Jerome?
Is it x cos squared x? Or just cos
No.
squared x?
No. The cos x is right.
2 sine x cos x.
That is it. 2 sine x cos x. So Jerome, maybe better put it that is then, because you realize it's actually a function of that power. So 2 sine x cos x. Just to make sure everybody understands how we get that. Remember, the chain rule says when you have a function, raised to the power, the same thing we did a while ago, multiply by the power, that's where the 2 came from. Differentiate the function inside, that's the cos x, and put the same function inside, which is the sine x, raised to 2 minus 1, which is the sine x to the 1, which is the sine x. So those three things occur. Power, that's a 2. The
And
function derivative, which is the cos x, and then the same function to the power minus 1, which is just sine x. That's where we get these three from. What about the last one?
So, sir, hold on, sir, can you hear me? Okay, sir.
Mm-hmm.
So you got plus cos x again.
Cos x, all right.
All right. Then you go right back the same something there again. 2 to the sine x.
Uh-huh.
And then you're going.
That's it. I say all right too. That's good. That's it. The most you can do is factor out the cos x, but can't do that. Much writing. So that's it. I saw next one now. This is the type that I like. That one of your that number 4 is obvious, but number 5 is nicer. It's a little more subtle. The 2 to the e to the x plus 2 to the e all raised to the x. Yeah, man. That's my type of thing. Differentiate that now.
You like this? All right. All right. Go help you now, sir.
Go on.
So you have e to the x. Bring the e to the x at the front.
Mhm.
All right. And then you're gonna have hold on. All right, then you got right by the 2e to the right by the 2 raised to the e to the x. ln 2.
You're smart. All right. I thought that's it. And then e, but all right, go on.
Oh man. Plus, all right, now put the x in front.
X in front.
No. That's incorrect. What? Don't put nothing here, sir. Erase that. Because the derivative. No, man, put it there, sir. Sorry. So x times 2e in bracket raised to the x ln 2 to the e. No, sorry, ln 2.
All right.
Wrong?
Little bit.
Ah.
What is the mistake? The first part is all right. This is correct.
You bring the x to the front. You're right, but the same thing, which is 2e to the.
I think is that part confusing, you know. All right, let me give you a hint. Fix up this first.
E ln 2 to the ex.
Go again.
E ln 2 to the ex.
Oh, yeah, e ln 2 e to the 2x. Oh, sorry. I think I said. Say it again one more time. E ln
2 times 2 to the ex.
Oh, 2 to the ex. Okay. So is the x in the power for the e, or where is it x?
The x
sir.
Beside the e, 2 to the ex, not 2. No, sir. Beside it multiplied by the e.
Okay. All right. Yeah, that is right.
Yeah, my mistake, sir. Sorry, not mistake. What I didn't see is the power to power rule. 2e to the x becomes basically 2ex, like he said.
Right, and that's what I thought that fixed up first. So it's actually going to be 2 to the e to the x plus 2 to the e times x. All right, so let me fix up this then. So just make sure everybody gets it. This one was correct. So this that Aki did first was correct. That's right. Remember, you differentiate the function in the power. You differentiate e to the x, you get by e to the x. So that's why they stay the same. And you always have to put back the constant raised to the power, which is where this comes back. And of course, times ln of the number, the constant, which is ln2. So the first one is fine. The second one, however, as we see, remember when a number is raised to a power, and you raise everything to a power, the powers multiply. So we get e times x, which is this. So to differentiate that now, and what Akin was doing was not quite wrong, but, well, I mean wrong, but it's not, what he was not realizing was this was a constant inside here. So it's not a function raised to a power, it's a constant. That was what was throwing him off. But outside here now, this one, we differentiate a number raised to a power, you differentiate the power. So we're going to differentiate the power here. When you differentiate e to the x, sorry, e times x, you just get e. Is that differentiating 5x? You get 5. Differentiating ex, you get e. So with the e, then you put back the same function, 2 to the ex, or 2 to the x, times ln of the number, which was 2.
Because
That's it.
ex here, e is being considered a constant here because you have ex.
Come on, e is always a constant, you know.
Yes, sir.
All right. But it's not e to the x, right? That was the difference in here. So that's my type. I like those because those make you think. I saw one more mad one, you know. I mean, just do them, yeah, just get them out of the way. I actually see 2 more that look interesting. I'll work out this one though, so go faster. Because I want to get
So for number
integration.
5, would we leave it there, sir? I would simplify it by putting
You could factor the ln too. Simplify that, you know?
the e and the ex to the power, sir. ln2, or don't do that.
The e and the ex. All right, tell me what to write. I'm not sure what you're saying.
All right, so we'd have 2ex ln2 ex raised to the power, sir,
2ex.
times ln2 ex as the power.
Oh,
sir,
you mean you like this? Okay. I get it.
Sir.
Go again?
No, I'm saying that he's trying to make it neater, sir. I like my mother, sir.
Yeah, I realize.
But remember, the first 2 is 2 to the e to the x, and the second 2 is 2 to the ex.
Yeah, but what he did was just carry this to the power. Right here.
Yeah, carry
Just
the
use
e to the power.
this is the log rule. Base power result.
And then for the other one, you would put the e to the power.
All right, that's not bad. That's not bad.
That's good, Jerome. That's good. Like that. Neat. Sir, that neat, sir.
Yeah, look beautiful. All right, what was the one I had right ago? Not bad, Jerome, not bad. ln, let me write again. Oh yeah, this one. ln x squared all raised now to the 2x plus 3. So this is a nice one now. This one test if you know logarithms and everything. So notice that there's a function and there's a function up here. Function below, function above. A matter of fact, I should give you one next, you know. I should give you something like this. X to the sine x. Yeah, I'll do that one next. Because, you know, I'll give you the rule so far where you have a number, not a number, a function raised to a power, like a number up here, x to the n, or x to the 5, or whatever. X to a function raised to a power, and I've given you a number raised to a function. But I've not given you a function raised to a function. We'll do that one next. Let's see how you approach it, if you can figure out what to do. All right, let's finish this one first. Boom, boom, boom. So, to differentiate this now, we have a function, ln x squared, raised to a function. But what makes this one not too hard, well, let me not say anything. What would you do?
What would you do? What would we do? Oh, all right. So, if you're going to all right, sir, it's going to be that the rule you gave us that the derivative of ln x, right, sir, is 1 over x. So the derivative of ln x squared is 1 over ln x squared
Oh, as I mentioned, that, you're not fully right. I forgot to show you my rule that I created, Thank you for no. What you're saying is not quite right. It's not 1 over x squared. It's not 1 over anything. If you're
Just a
differentiating
try,
n, no, but you were doing bad. I'm at I'll do an next question before I do this one, so you can see how to differentiate, because this is the same function to function, but I didn't realize that the x was raised to the power. I thought the x was like this. When I was giving you the question, I thought it was like, actually, I forgot the bracket was there. I thought it was like that, which is easy to do. Just carry on 2x plus 3, but that wasn't the case. So I'm going to do one more before this one, because it's going to be more involved with this one. But before I continue, if you have ln x raised to a number, let me show you something quickly, see if you can catch a pattern. If you have ln x raised to 2, differentiate it, you're going to get 2x paramètres derivative above the function. You can check what it breaks down to. I won't tell you if you don't see it. Ln x cubed, differentiate that, 3x squared over x cubed. One more. Ln x to the 6, or 5, use 5. Differentiate it, you're going to get 5x to the 4 over x to the 5. What does the first one give you? One up here.
So all you do is just find the derivative of the function. Oh, what's the answer? 2 over x.
2 over x, right? What about the second one?
3 over x.
And this is?
5 over x.
So here's my quick rule now. If you have ln x to the k, where k is an integer, of course, positive integer.
This is k over x.
K over x. That's what I was saying. When you differentiate ln x squared over ln, it's just 2 over x. All right. So it's not really a rule. That's why I say. That's why I just call it my thing, because I just realized
it's just a trick, sir.
Faster. Yeah, because it's a trick that make it work quickly. Ln x to the 40 is 40 over x. All right. So before I work with number 6, I'm going to give you a different number 6, and I'll come back to it because I wanted to catch how to do it. You're going to have 2 ln's. That's why I don't want to do it that way. I don't want to do it.
Minimize that, sir. Sir. The one you just delete a while ago. Undo and make it small and put it to the side.
We want it? Okay.
Not necessarily, but remember, other person might need it, sir. Just minimize that, go to the side. Like you always do. Yeah.
So missing. Oh, the x. If it's the x gone.
Oh, it's all right. We know it's x. All right.
All right. So this one now, I'm going to soon go back to number 6. I'm going to do one like it, but a little easier first. So the question says, so when you got number 7, I'm going to get back to it. Find f prime of 1 if f of x, it's a trig function, but the method is what you need to know. X is sin x. All right, so it's function to function. There's a specific method I gave you. Let's call it f of x y. I'm going to say f of x, no matter. F of x equals x to the sin x. Now, you have not gotten any rule for differentiating a function with a function. You got rules for number to a function, you got rules for function to a number. So since there's no rule you can use for function to function, how can you break it down before you differentiate it? Well, I thought you do something. What would you do to get it?
Substitution, sir.
No, not substitution. Something else.
And it's not chain rule, sir.
You learned it. I want to teach it to you. Is last class or the class before?
Give us a hint, sir.
Well, it was taught to you recently. Either last class or that class.
That's not even. That's crazy.
The thing right before exponential.
Exponential.
What will it right before exponential?
Jaja.
Starts with L.
Oh, we know what you do. You take the natural log of both sides.
There you go. So take the natural log of both sides.
At the clue you're saying now, because you say it starts with L. I didn't know it was that.
I'm to the third, we did right before exponential. All right, so it's ln f of x. What's going to happen on the right side though?
Oh, you're gonna have you're gonna split, sir.
What is a split? What do you mean?
The natural log of. Oh no, better.
You put sin x as the base, sir.
Well, not base, but you put it at the front.
Yeah, base 4 results. Yeah, base 4 results. So
I'm
yeah,
asking, when you said base, Jerome, that's what you meant, Jerome?
That what means. Accidentally
Oh.
call the base the front, but that's what it means, sir.
Okay, good. That's right. So differentiate both sides now. We'll differentiate left side.
Y over Y prime. Y prime over Y.
So we don't really have no y, so where to put it then?
Alright, so F prime of X over F of X.
Correct. That's what I make sure you know is that. All right. Well, you're right. Y for y. What's on the right side now?
Sin X over X.
All right, you do ln first. Plus.
Plus C.
Eh?
No, wait.
Remember, says product rule.
Right. That's what I thought you did this one first.
Oh, sir, me never see product rule.
Guessing.
Oh,
Is that a good guess though? Right.
me never see the product rule. Harold, me never see. All right. Anyway, sir. So the first. Sorry, the normal way, sir. The normal way. The derivative of the first,
Which is
time,
what?
which is cos X, times the second, which is ln X, plus
And then
leave the first one alone.
that's what I say you're right, you know. You got the second one. That's the second one. This
I guess, sir. I get it right. I guess, me guess.
is a good guess, Mr. Tell you. Because times 1 over x. When you finish ln x, you're going to x.
So leave the
That's what
second
I'm
first one alone. And then we have 1 over X, sir.
Mm-hmm.
Yeah.
That's what you call a supreme buck-up. All right, so remember the question was to find f prime of x. F prime 1, beg your pardon. So we need f prime. So I'm just carry this on a little further. Soon come to you.
So when I can just put the f of x right away instead of right, so f prime of x equals that's something up at top. X sine x raised to the sine x. Open bracket. And put back all of that something there. Just duplicate, sir. I'll waste time, I'll go right back. F prime of it and then the next line. All right, now, so you're gonna end up with So we're gonna distribute.
Yeah, put the one reverse today.
Okay.
You're going to see what the answer is. That's nice and simple. But let me see if you can figure it out. It's equal to one solitary thing is in here, so. A lot of things going to disappear.
1.
Yeah, no, it's not 1.
ln1 is 0, so cos 1 times 0
Mm-hmm.
plus
That's the answer we want to know. We're not writing them down. And it's equal to one thing that is inside there. Or I shouldn't say inside there, but one thing from this. It's either this one, this one, this one, this one, or that one.
So we're not like gonna do this. No,
A simple thing, man. A simple thing. If you look at it properly, you realize.
1 over 1 is 1. Sine
Mhm.
1, sine of 1 is 0.
Mm-mm.
Sine of 1 is not 0.
Mm-mm.
A cos 1 is 0.
Well, you see, in this case, because we're doing radians, it's not going to be like that. If it was like, what you're thinking about is pi and not pi and so. Cos of 90 is 1. Sine of 90 is 1. Cos of 0 is 1.
sine 1 is 0.841.
Well, I don't want to round it off. Look, all right, let me just work it out with you quickly. Got time. What's 1 raised to the sine 1?
1, sir.
Correct. 1 raised to any power is 1. What is the cosine of 1? We don't know. We don't care either. Because what's n of 1?
0.
Good. What's 1 over 1?
1.
So when you do all of that, what is left?
1.
Look again, man. What's 1 to the
Sine
sine
1.
1?
Sine 1, sir.
Correct. That's all I said. Sine 1. Which is some decimal.
Oh my God. Oh, okay. So I'll go on.
Yes, it says 1 times cos 1 times 0.
I'm sorry, but
Plus
for
sine 1.
the end part, sir, why would never just stick with the sine x over x? Like what Akeem Lisa first. When he did guess.
That's fine. That's why I said he wasn't wrong, but because people might not know how you got it a split and for you to see. Well, sine x of x was right.
Jerome,
So
this is about it. We didn't even know how we get it. That you talk about. We didn't even know how we get it.
Right.
You got it
But
right. And it's
yeah, but
easier for
he was
work,
fine.
so.
He was right. So that's right. But I split it to make sure everybody see how we get it. Leave this alone, differentiate that. We don't have to do it. Sin x of x is fine. If I was doing that as sin x of x, that's why I say he was right when he said it. But because people were not so sure, I showed it to you. So the way you know, so the answer is just sine of 1. When you do your questions, you get something like this, just write sine 1. I like exact answers. I don't like the rounding off. If you run off your question answer, I'm going to run off your marks. Just leave it like that, sine 1. All right. Now, let's look at this one. It's the same process. That's why I showed you that one first, because it's a little easier. Okay, let's see two little simple functions. You take ln of both of them, you get the x and sine x. But for this one now, we have a ln of something raised to a power again. But the problem with this one now is that,
No, go ahead, sir. Sorry.
problem with this one is you're going to get ln of ln. So if you take ln of both sides, you're going to get ln of ln x squared. Don't panic, it's fine. And we differentiate both sides. Well, before differentiate, carry it down. So you're going to get so now it's ln of a function raised to a power. Well, if you can spot that. It's like ln of 6 to the 4. So which is a 4 ln 6. So it's ln of a function in bracket here raised to a power. I'm going to take this power to the front.
Okay. So go have 2x plus 3 ln in bracket. No, enough in a bracket. ln x.
You better put the bracket.
Okay, ln x squared.
No,
Oh,
there's
yeah,
a mistake here. What is the mistake? I purposely wrote the mistake. What is the mistake?
Oh, one bracket, sir. You need our curve bracket between the two. Right.
Okay. And make sure you write the mistake so that when you write it in the test, and until somebody lose marks for it, you can see it from now. Because it's wrong without it. And students number say, sir, how that's wrong, sir? I say, okay, what is 2 plus 3 times 5? They say, 17, sir. I say, good. What is now? Is that the same 17? So please put your brackets. I'll mark it on for it because it's wrong. If you write something that is incorrect, you're going to lose marks. All right. Continue this now. Let's differentiate this now. Both sides. Left side is easy. Y prime over y. What's happening on the right?
Isn't a product rule?
Yeah, man, product rule is right. This is one function and this is the other.
All right, good. So derivative of the first, which is 2 times, so it's 2 ln and put the other ln x squared in brackets, sir. Plus, leave the first one alone. Put it in brackets, sir, because I take off marks. I go to do the derivative of the second.
And this me want here though.
Hold on now. Sir, teach for this, sir. Remember you teach for this.
Just follow the rule, man. It will be all right. Come, people, help him. We're differentiating this.
Eleanor, no.
Jerome, I want trick and show you last class. Just.
All right, let me make it easy for you. What's going to go down here?
The function, x
Which
squared.
is what?
ln x squared.
Correct. So I'll go to the top.
Oh, because it's the natural log of a function. Oh, so ln x squared.
And the ln go top, sir.
And
the ln go top.
Oh, me know what got up, sir.
What?
2 ln. No. It's not 2x.
You're close.
2x ln.
No.
All right.
Think
Stop.
of the shortcut I'll show you a while ago.
I hate guessing. I'm done.
So if what is supposed to go to the bottom, the function that you're going to differentiate.
So it's going to be the I. So the rule you teach us is that the derivative of the function over the function. That's all.
There you go. So if this is the function, what goes above it?
The derivative of the function.
Which is what?
1.
What you say?
The derivative of the function of 2x.
No.
2.
No.
All right. I'm done guessing. The derivative of the function.
This is the function, you know.
ln x squared.
Correct. The function is ln x squared, not x squared.
Oh, 2 over
So
x, sir.
Who's that again?
2 over x.
There you go.
Oh yes,
I
because
ain't just sure. I ain't just sure.
Yeah, man,
Mr.
just wait
Wagwan,
here.
man.
Man.
So
I was
sorry.
going to say, you know, I just, matter of fact, I did say it. But I was going to go back up here and say, see that, so? I was going to do that.
Mr. Wagwan. See the ln x squared, you bring the 2 in front of the ln x squared that is in the bracket. You bring the 2 in front of the ln, and then you find the derivative of ln x, which is 1 over x. And then
Well, you
put
can do
it.
it that way. You can do it that way. I just remember the thing I
Mr.
showed you, 11 x to a number. But what I really wanted to catch is what people normally struggle with is ln of ln. That's what people normally get a little problem with. So to make sure everybody gets it, we're differentiating ln of a function. The rule says, when you differentiate a function, you put the derivative at the top of the function and the function below. The function in this case is not just a normal x raised to the power type of thing. It is actually ln of x squared. So that goes to the denominator, and the derivative of that whole thing goes to the numerator. So differentiate ln x squared, which gives us actually 2 over x.
Okay.
So let's simplify everything now.
I have a question, sir.
Go ahead.
I can just explain it though. What happened to one of the ln?
This ln here, or this one?
No, the first one is circle, sir. But I feel like I just explained it.
All right. Remember, when you differentiate ln of a function, you're getting derivative over function. Notice there's no ln.
Oh, I get it, sir. I get it. As I'm saying, you just explaining about whenever to see.
No problem, man. Because sometimes a whole bunch of different things happening one time, so you might miss something. So when you differentiate, that goes away.
I have a question. Go ahead, but I have a question.
All right. So let's simplify this thing. So remember, we need to find y prime, which is going to be the whole of that madness there, ln x squared raised to the 2x plus 3 times everybody. Should I simplify it? I can't try thing is. So we're going to get ln of ln x squared squared. So I brought this 2 to the power here. And then now we're going to have 2x plus 3 times 2. I'll call it 4x plus 6. 4x
Over
plus
x ln squared. Over x ln x squared.
Does anything cancel? Let's see. Oh yeah, this can cancel this, but the problem is we have a power minus 6. Look at that. Yeah, that's it. You want the question? Is that a question, Aki?
Yeah. How do I pick up on the technique you just showed a while ago, where we find the we do the natural log of both sides? I think you might have said it in the last class, but how do I look at a function? I know that this is the approach I should take.
Whenever it looks difficult to differentiate the other way. Because when you have like a lot of functions over an x function, product of functions over product of functions, that's the best approach to simplify it. Also, whenever you have a function raised to a function, that's almost the only one you can use.
Oh, function raised to a function is a key one.
Right.
Okay, function raised to a function, natural log of both sides. All right, sir. Respect.
Yeah. All right. Let's go to integration now. We have some time. Let's see, 30 minutes left. All right. So that's all the hardest ones I could find. Let us know. I was looking to make sure I didn't leave out anything. We have one here, x squared plus 1 to the ln x. I think if you, the ones that we do so far, I should be able to help you with it. X squared, what? The x squared plus 1 raised to ln x. You guys can do that, right? I don't need to go through
Yeah.
it. Because this one look harder to me. One of those look harder. I know what?
So is it
We're not hearing the
equals-
answer. Try it. Sorry, where's it, Akin?
No, sir. I was asking if it's y equal to the. Okay, right.
Try it. No, I'm giving you 3 minutes. Well, 4.
Oh, we must do it now. Oh,
Yeah.
okay. So not far. Sir. Sir,
Finish?
something, but he won't. I'll give you the because of time, sir. I'm going to give you the answer that I got unsimplified.
All right.
All right, sir. When I did the math, I realized that we get another ln of a ln function. So my answer is x squared plus 1 in bracket raised to the ln x. Sir, now
X squared plus 1 raised to ln x.
open square bracket 1 over x.
So like a long one. Hold on. I'm going to space.
Yeah, I'm gonna simplify it still, but through a time, sir. You know. All right. All right. So open square bracket. 1 over x. Open another square bracket inside, sir, or curve bracket, whichever one. ln open bracket again, x squared plus 1. Close the inside square bracket, sir. Plus ln x open bracket again, 2x over ln open bracket downstairs, x squared plus 1. Close bracket, close square bracket. That's
That
my
we get
answer.
it, sir.
You see anything?
Yeah,
Yeah.
that I have, sir.
But this
Yeah,
can
so-
simplify it, so because of time, I'm gonna simplify it.
Yeah, man. It's all right. It's going to be similar to this one. Okay, no, it's a function we started with before had ln x down here, and the function up there. This time
Yes,
ln x
sir.
is up
Same
here.
thing as well.
Okay, it seems right. Based on what I was thinking in my head, because I didn't work it out, but it seems similar to what I was working out in my head. All right, not bad.
Sir, what's that? Oh,
Quite possibly. You have some in the bank there, right? So you know what? The answer. Okay. Integration time. Now, to spot the integration for e to the x functions, you have to have either a function raised to a power, sorry, you have to have a constant raised to a power, somewhere, somewhere. So the general rule is if you differentiate y equals a to a function, you differentiate that, you're getting the function derivative times the function, the constant raised to the function, times ln a.
LNA,
So if you're
right?
doing reverse, if you're integrating, these things are going to like, this is going to go back up to that one, and the LNA is going to disappear. But generally, you're not going to see the LNA there. So generally, what they do is put it like this. The general integral for the derivative of function, remember LNA is a constant, times a raised to the function. So since it's not normally going to be there, you're going to just have the a to the f of x over LNA plus c. So then how did I get that? Because think about it. If you differentiate this now, these two things are going to come back. So you're going to get f of x right here. You're going to get LNA at the end. But the LNA at the end is going to cancel this one. So you go back to this thing over here. If you're confused about it, let me show you an example.
Yeah, okay, Mr. One.
Number one. So if you're integrating, let's say 2x times 5 to the x squared. Based on the rule, you're just going to get 5 to the x squared times ln of 5. Oops, divided. I'm differentiating again. Over ln 5 plus c. Now, if you don't see that right away, what you can do is say, so this is the answer. But if you don't spot it right away, whenever you see these type of questions and you don't get the answer right away by looking at it, then the long way, which is to, and this always works. Make sure you cancel what differentiate to give what, Obviously, this differentiates to give this. So you're going to say, let u be equal to that thing that differentiates to give the next one. Which is therefore du, because sometimes the 2 is not there, so you might have to do it long way. If you don't, if I showed you shortcut before, but just do it long way first, and let me show you everything. Differentiate du with respect to x, you're gonna get 2x. Obviously, 2x is there, so you can just multiply both sides by dx only. And that will give you what you have up there. Therefore, du is equal to 2x dx.
We have that exactly, sir. We have that exactly.
Right. So therefore, the integral of 2x 5 to the x squared dx is equal to the integral of, replace the 2x, the x squared, beg your pardon, with u, right, 5 to the u.
Times u.
Right, because these two things are du.
Okay.
And as for the rule now, the rule says, if you're integrating a number raised to a power, or give it this whole thing, no? Or should I give it the general one too? Yeah, kind of something I'm confused now. Right, whatever. Integrate a number raised to a power, you just divide by because this is the thing, is when you differentiate u, I should give you this rule as well. Instead of put the whole f of x, the integral of a to x is just a to the x over a ln a. Because I don't know most of you realize that when you differentiate u with respect to u, what do you get?
1.
1. So that's why it still matches the rule up there, it's just that it's not so obvious. Because this time the derivative of f of x is f prime of x, derivative of u with respect to u is just 1. So the 1 is actually there, just don't see it. So I should have given you this one as well. The general one plus the shortcut one. Anyway, whatever. So this gives you 5 to the u over ln 5 plus c, which is not our final answer because we don't know what u is. Because in the last number u, so put it back. 5 to the, what's it, x squared?
X squared. That's the x squared.
Ln
Over.
5, right. Which is the same thing we actually got right here. So if you see it fast, if you can see the derivative and you see the thing right there, from a general rule, you can just go straight to that answer right there. If you don't see it, you have to go through this process.
So it's easy to go through the substitution because not all the times, like you gave us the example in class, not all the times derivative of the
It's
function
obvious.
was obvious. So if you use the
Matter of fact,
substitution rule,
if I give it to you, it's not going to be obvious. The derivative, well, I mean, one might be x squared and one might be x, or one might be x cubed and is x squared, but you're not going to see the number pretty like that. 2x. Sit down nice for you, no, sir? If we can figure it out, when I work it out. But I was saying, let me show you something quickly. I'll give you a two-way one. Very shortcut. If the number is not there, let's say number 2. Let's say integrating. Oh, let me put by the rule. The shortcut rule. Not shortcut. The one the book has. The book has this one. One thing I don't like about these textbooks, they don't give you the general rule, the function itself. They give you the simple x. So if you get the function, you get stuck. So I like to give you the general rule, which applies to everything. But the rule that the book has is just a simple one, which is this: the integral of a number raised to x with respect to x is just a number raised to x over
natural base.
right, plus c. So that is the rule without the up here being a fancy function, just x. And the reason for that is because when you differentiate x, you're going to get 1. It's actually the same rule, just a broken down version of it.
Okay.
All right, so back to number 2 now. Come on, number 2. All right, which one I can do now? Let's do, where's the questions? Here's one. No, that one is too easy. Let's do this one. The integral of 5 to the root x. No, but that one, no, well, I'm going to do that one last. It's a tricky, easy one. 10 to the 5x minus 1. Do this one first with respect to x. It might not be so obvious right away, but generally, when you're doing these type of questions, the derivative thing up here is going to be multiplied right here to some multiple of it. When you differentiate 5x minus 1, what do you get?
5.
5. So you can see that it's just a multiple of this number right here, 1/5 of it. So we can say let u, oh, by the way, yes, shortcut. I'm the shortcut afterwards. Let u be equal to 5x minus 1. Having done that now, differentiate it. Get 5 as you guys correctly said. And divide both sides by 5 because there's no 5 right here. So divide both sides by 5, get rid of it, and multiply both sides by dx. Now that is there. We have dx can be replaced by dx. And 5x minus 1 can be replaced by u. So that means that this integral of 10 to the 5x minus 1 with respect to x is simply the integral of 10 to the u. Because dx gets now replaced by...
Where's the 1/5?
I'm not put it here, I'm not put du here.
Oh, okay.
Because I want to put it outside, so I put it last.
Oh, all right.
Replace the dx now by this. So because everything is taken care of, the 10 to the 5x minus 1 is 10 to the u, and the dx is 1/5 the u. So it's 1/5 the u. You can integrate that easily based on the rule.
So it's just u of ln 10.
Is what?
No,
It's 10 to the u over
ln 10.
right. Let's see. So our final answer is no, but I go try to divide 5 into 10 and get 2 to you, you know. Mr. Going mark on to that, see? Anyway, it's going to be, well, if I can make it look pretty, yeah, I can make it look pretty. It's 10 to the 5x minus 1 over ln 10 to the 5. I was going to write 10, like what, 100,000? Too much number. Yeah, that's it. Too many zeros. Oh, here's what I was saying. When I'm doing these questions, I'm going to come out along something there. So I found a way. Look at this. The integral of 10 to the 5x minus 1. As you guys correctly said, I don't know if it's 2 voices I heard or just a key, but it's only like 2. When you differentiate 5x minus 1, there's a 5. So if we had that 5, it's an easy integral. So put the 5 there and divide it outside here. And we know that based on the rule that I gave you, the general rule, when you integrate that, is just the number raised to the power over ln of the number. So it's simply going to be 1 over 5 that was outside the bracket there, number raised to the power over ln of the number. Done. That's how I do them. I mean, but I'm used to it, so it takes so I finish in like 1 line. But this method, make sure you understand it always works because it's not always going to be as simple as this. And you might not be able to spot it right away like I can spot it. So ensure you understand the substitution. If you want, you can do it like this. A matter of fact, since I created that thing, I saw it in a couple of textbooks. I don't know if it was always there, but I didn't know. But I figured out that this way will work. So you guys can try it if you want. If not, make sure you can do the substitution. It might be longer, but it will work. These questions are not, they're worth a lot of marks too. So
Sir,
sure you can do it.
the long way is always a nicer one for me.
Agreed,
Long
Harold.
way has everything steps and everything is good. So
I
don't
agree.
use it unless you understand it. That's why I don't teach it. A matter of fact, because I see you guys understand the calculus a lot better than most students have had. That's why I show it to you. And I don't know when I show it to students.
Yes, sir. That second way is boring.
Yeah, me not like shortcut, sir.
It's because I do actual science exams and so I have to work fast. I have to know
Yes,
those.
sir. I know the timing.
Yeah, man. It's a 4-hour exam, 30 questions, but trust me, time run out. All right. So let me just ensure that this is not taken as the main step. The main thing is to put up this up. Make sure you can do it. This is just shortcut, and there's somebody that said shortcut draw blood. Well, in this case, shortcut by draw marks, we get it wrong. So make sure you can do it upon. There's the one more.
It's a shortcut, John Marks.
If you're wrong, I've go ahead. Because it's the thing, good thing about doing it a long way. If you make a mistake along the way, I can see where it is and I can, give you marks for what is going on. You do shortcut, I don't know where you do, and it wrong, it just wrong. All the marks
Exactly,
wrong.
sir. Exactly. It's not about the answer, sir. It's the steps.
Method, right.
Yeah.
Sure that you understand. All right, let's do this one here. The one I was going to do a while ago. Integral from 1 to 4 of 5 to the root x over root x dx. It looks complicated, but it's actually easy. As long as you know the derivative of root x. When you differentiate root x, what do you get?
Half x raised to the minus a half.
Simplify it. You're correct. Simplify it.
Half x raised to the minus
me, right? Half x minus half, which is what?
over 2 root x, sir.
So go again.
1 over 2 root x.
Correct.
1 over 2 root x.
Good. So that should give you an idea of that this derivative is actually down here. So those are 2 missing. So having seen that, let u be equal to what?
Root x.
There you go. Because by differentiating the root x, you get back the one down here, which is actually x to the minus half. It does have to be below. So you might not realize that it's below. That's why sometimes that students rewrite the thing to ensure you see everything clearly. It will actually be this. This is actually the integral from 1 to 4. Oops. of 5 to the x to the half, or 5 root x, times 1 over root x dx. So this thing here will give us the u. The du, beg your pardon. Well, what is this? So let's differentiate the root x. Remember, root x is the same as x to the half. So as Akin correctly said, when you differentiate it, you're getting 1/2 x to the minus half. Of course, the 2 is not there, so we'll get rid of it. Multiply both sides by 2, and multiply both sides by dx always. So du is equal to x to the minus half, or 1 over root x dx. Right, so over here as 1 over root x dx. So everything should be clear now. So this is that, which is right here. Not finished yet. We have some numbers now. When x equals 4, what is u?
2.
2. And when x equals 1,
1.
1. Everybody okay with that so far? Yes, sir. Lovely.
Yes.
Moving on. All right, so we're going to have the integral from 1 to 4. So we rewrite the whole thing. 5 to the root x, 1 over root x dx. So it's integral from 1 to 2. We're doing replacements now, substitutions. 1 to 2. We have 5 to the root x, which is 5 to the u. Remember, u was root x.
Times 1 over.
Right, times what?
1 over u.
Well, I mean, it is 1 over
Sir,
u. Yes,
the
1
1 over
u.
root x.
Yeah, but we're using this.
Oh, sorry. 2 du.
All right.
2 du. So put the 2 outside and the other. Right. So yeah.
All right. So we have 2. When you differentiate, when integrate 5 over u, 5 to the u, what do you get? I want to get used to
5
it.
to the u over ln 5.
Correct. So I'm going to put ln 5 outside. If you want to put inside, it's fine. 5 to the u over ln 5, same thing. I'm just going to put numbers in there now. So we're going to get 2 over ln 5 times 25 minus 1. Oh. Damn, yeah. Sure everybody see it? So the answer is 40 over ln 5. Any questions?
This one needs some revision. Just run back to the recordings and just.
You better run back to it, because these can be, you see them one time, say, okay, I'm getting it. You leave it alone. See, I think getting test, you probably wonder what the back foot is that. So make sure you practice them.
Sir, I go through all the recordings. After the class, I watch back every one of the recordings.
That's a good idea.
That's what I do.
And when you're doing them, like, you try to do the question by yourself before watching the full thing. Like,
That's what I do, sir.
okay, good idea. Send me one more thing. No, what time is it? 7 minutes. Give me one to try.
Wait, sir. 5 square minus 5, 1 is 5 to the 1. And
Are you
then,
writing?
no, sir, I'm saying 2 over ln 5 times 5 square minus 5, 1, and then you get a 40 over ln 5.
Mm. Did you ask about it?
Yes, sir. Outcomes.
Because 5 squared is 25.
Yeah,
25 minus 5 is 20.
20. Oh, so 2 times 20.
2. Yeah.
So,
Yeah, man. So homework, not graded, of course. I was on number 3 or number 5 or 4. 3. So try number 4 on your own. Next class, you can let me know what to get, if you get it right or not. It's the integral from 0 to 1, 10 to the 3. Wait, now the zeros. 0. All right, slowly. 10 to the 3x. Is it plus? Yeah, plus 10 to the negative 3x with respect to x. So you're going to get the answer that is just a number. So let me know what number you get next class. All right?
Okay. Okay, sir.
Yeah, man. So if you have any questions right now, let me know, and then you can just let me know where you get for that next class. No questions. All right. So stopping here then, people. See some of you again in linear algebra. For the rest of you, see you next week.
Yes, sir. Take care.
Yeah, man.
All right, sir.
Anybody exporting, or I can just close?
No, sir. Export, sir.
All right.
Export, sir. Export.